So the next one we have is, of course, now a a linear distributed load, not a constant. And we're asked to find the internal forces at point C. So we'll go through the same uh, setup, right? So step one, divide and conquer. So we'll go ahead and make our section right here. And then let's look at both free body diagrams and figure out what's going on. So left-hand side. All right. So we have some portion of the distributed load. Let me scooch this down. And we know up here, it peaks at the 1200 newtons per meter. And it comes down to some value. We'll figure that out later. And because we have a fixed support on the left, right, then we know we're going to have an AX, an AY, and now we have a moment here. Our internal forces are going to generate N out tensile, shear down, and then we have a moment at C. Now let's look, and what are we missing? A coordinate system. Now let's look at the right-hand side. On this side, we have whatever's left of that distributed load that goes down to 0. So because it's even, we know that this is just going to be a triangle, right? 1200 newton meters here on the left, 0, right? So halfway in between, this must be 600 newtons per meter. Right? This is just a line. So we know this is 600 newtons per meter. And now we have our internal forces. Normal tensile, shear up for the right-hand side, and then a moment concave at C. So hopefully everybody agrees that the free body diagram on the right seems to be the easier one, right? So let's use that one to apply our equations of equilibrium. So we'll use this for the right-hand side and using that free body diagram there. So let's go ahead and simplify first that free body diagram by replacing the distributed load with an equivalent force. Right? So this is where all of your training so far, right, comes into play and comes together. So in order to get the equivalent force for the triangle, we basically just need the area of that triangle, right? So we're going to take this force. So we have the 600 newton meters. So the area is equal to 1/2 the base is 1.5 meters times the height, 600 newtons per meter. We should come out with newtons, 2, 3. So we have 450 newtons. And where do we apply it? We apply it 1/3 of the way from the base. Right, so that's going to get applied right here. This is 1.5 meters, and it's 1 meter from the right side or 0.5 from the left. It doesn't matter. So 450 newtons. Let's just say this is 0.5 and this is 1 meter. Like so. Now we can go ahead and just solve for the equations of equilibrium. Again, encourage you to pause, make sure this is pretty clear to you, and then just use this as a good opportunity to come back and check. So sum of forces X. N equals 0, we can see right away. Sum of forces Y. We have V up minus the 450 newtons. And then sum of moments, I would pick again at C, right in the middle, keeping it simple. So 450 for our convention is going to be a negative moment convention, negative 450 newtons times 0.5 meters. And then the M is negative as well. Sorry. So M, in terms of the magnitudes, Normal force is 0. Shear, so this should of course be equal to 0. Shear is equal to 450 newtons. And then M, the internal moment, is equal to negative 225 Newton meters. Which means that the moment's actually spinning the other way. But we can leave that alone for now. All right, one more, and then I think we're done for today.